So actually, I'm going to report an experience we have done in the framework of a European project dealing with the application of UHPC in basins and tanks for geothermal power plant. And I would like to start this talk with a reflection. This is a paper, a reflection paper, which has been published at the end of September by the European Commission, addressing the role of materials in the post-COVID society. There is a nice sentence, I think, that involves all of us as civil engineers working with advanced cement-based materials to think of the contribution that we can bring to create a less dependent, more resilient, well, this is written European because the author is European Commission, but it's world economy by guaranteeing raw material supplies, ensuring higher materials durability, higher energy efficiency, higher degrees of material recycling and reuse by material saving through optimized products and design with enhanced repair. So this is really something that we can contribute of, and UHPC is an excellent candidate for this. I have selected this topic, geothermal energy. We do know that we are going towards a no carbon economy, a big transition throughout the world, and geothermal energy is surely one of the renewable sources. Nowadays, there are regions in Italy, you can see in Europe, sorry, you can see in the map the orange zones, and there is a program to go towards a higher and higher increase of the capacity of this kind of renewable energy. Obviously, besides the technical part of how we can harvest energy, there are also infrastructures that need to be built in service of these power plants. And most simple of them are the basins that are in service of the cooling towers for the water, which is part of the geothermal drilling and then has to be reinjected into the ground in order to avoid soil settlement. So this is a typical example of this structure, which has obviously to be designed complying with the conditions for durability for extremely aggressive exposure, because this water that the structure has to contain, actually they contain chlorides and sulfates, and these aggressive conditions are labeled as XS and XA in the Eurocode and the FIB model code. So this is a typical structure, this is a typical design, not much high reinforcement, but the issue is that because of the durability issues, these walls have to be made 40 centimeters thick in order to comply with the requirements. So there is quite a huge burden. And what is the service condition? Well, actually, this is how the water cools down simply by raining. And this happens really 364 days per year, because the tower is stopped only 1 day per year, and the basin is emptied and a little maintenance and cleaning is done. And this is what happens because the water is extremely aggressive. You can see which can be the conditions after years of operation for these structures. So actually, we gather at Resilience Consortium. This is the acronym of a project we have been working now for more than 3 years, and I've presented the steps of this project throughout the past convention, both in presence and virtually. And we are 13 partners from 7 European countries, encompassing the whole value chain of the concrete construction industry. But actually, we started, I hope this works, the movie. We started from our long-time lab experience on UHPC, dealing with the capacity to induce multiple micro-cracking and also investigating the self-healing, and said, okay, let this be the starting point and let us see how we can engineer the material in order to have enhanced durability, which really are targeted to the conditions that we have to meet in this application. So we have been working with dispersed steel fiber reinforcement, but also with micro and nano functionalizing constituents, nanocrystals and nanofibrils of cellulose for self-curing, alumina nanofibers as nano reinforcement, and crystalline admixtures for self-healing. And as a matter of fact, we ended up with different mixes, typical composition, 600 kilos per cubic meter of cement, slag in a 50% volume replacement, water binder ratio 0.18. We used 1.5% by volume steel fibers and different types of admixtures, as I've said before. Some macro images of the alumina nanofibers that we have been using, or of the cellulose nanoproducts. I will be back on this a little bit later. So we performed an extensive mechanical characterization of the properties of this material because we wanted to identify the design material parameters bending test on deep beams or on thin beams in order to replicate also the issues of fiber dispersion that we expect to have in some of our structures. We performed direct, well, it's indirect tension test, is the double edge wedge splitting you can see on the left, which we validated as capable of providing directly the tensile stress-strain constitutive relationship. So we identified different strain hardening or elastic plastic relationship from this double edge wedge splitting test, and we used them to simulate the flexural test both on deep beams and on thin beams. And you can see the orange, purple, and green curve who replicate either the upper bound or the lower bound of the response. And there is also an elaboration on how the neutral axis depth evolves in these specimens along the test. Well, then we went to the design. This is a structure that we have built. This is a finite element analysis for the ordinary reference reinforced concrete solution. You can see that stresses are quite low. These are tensile stresses in concrete, are quite low anyway. With the reinforcement that we provide, they are well kept. Then we designed two alternative concepts, structural concepts, only with UHPC, with no ordinary reinforcement. This is a 6 centimeter thick, only UHPC structure, and you can see the expected tensile stresses from a finite element analysis. And if you compare the design, stress, strain, and stress crack opening low, you can see the red dots are where these stress levels are on that constitutive relationship. So we are in the strain hardening regime and well below the strain hardening capacity of the material. And we also provided a partially precast solution in the sense that we precast 1.5 wide square slabs, only 3 centimeters thick. And then we installed them and cast in place some columns or buttresses. And you can see here also some kind of optimization of the stress level, because on both sides of the slab, the material works at more comparable levels. Well, actually, this is a slab. This is a statically redundant structure. So we made also a yield line analysis and found that the basin has a depth of 1.5 meters and found that actually it could withstand an overload up about 2.3, 2.5 meters. So from the structural point of view, we were quite safe. Well, we built on the site a specific batching plant, and you can see here a casting day, a typical casting day of the material. We cast two of the slabs. You can see the consistency and how it is also able to go around the corner. In this case, one of the challenges you can see here in the picture was also the design of the formworks and the installation of the formworks. These are some pictures of the structure now in operation with geothermal mats or geothermal water, and some examples. You can see the an ordinary reinforced concrete solution. Well, actually we were here with 10 centimeters, then we go to 6 for the intermediate solution, and then we go only to 3 centimeters thick for the precast solution. This is a picture which was taken last year on February 13, 2020, was just before the lockdown, and the construction was completed on February 21st. This is a picture. We made some filling and loading test on August 1st, 2020. And just a few days ago, I went back to check the health status. And you can see here a typical shrinkage crack, which was healed after some months in operation. Well, what's the point now? We do all know that this material comes at a quite higher cost at the time of construction. But shall we really think only at time zero of the life of our structure, or shall we go behind this concept? And also, shall we go beyond the euro per cubic meter framework or dollar per cubic meter framework? Because we do not make 1.1 by 1 meter cubes, we make structures. And we also have to evaluate how the performance of the structure evolves over time in order to be able to evaluate the service life. So what does this mean? Well, we do know these walls work like a cantilever. We know how to calculate the design bending moment and the moment resistant capacity. Well, actually, we have a permanent load partial safety factor on the action side, 1.35 according to the Eurocode, but being water, the load, we can interpret this as a surcharge level. So we end up with this surcharge level. Actually, our structure could have been designed for almost being completely filled, 1.45 meter. It never happens like that because there is a valve in order to avoid this, but it will be safe in this case. How did we design the moment capacity? We followed the Eurocode, we followed the FIB or the ACI 544 for our approach. So we use an elastic plastic approach in tension and also in compression with very simple force and moment equilibrium equations. And we were able to calculate the resistant capacity. You can see that just some numbers to reflect. Compared to a 5 kilonewton meter per width of 1 meter, which is the acting bending moment, we can guarantee a resistance of about twice as much. But then the durability comes into place. What does it mean? That, for example, there is a chloride attack and chlorides penetrate. We use a very, very, severe approach in the sense that as long as the chloride critical front penetrates, we remove that layer. So actually, we calculated the evolution of the resistant moment capacity over time by subtracting from the initial thickness the chloride penetration front. Or if we deal with sulfates, we have in the models a leaching model or an erosion model, and we employ the same approach. So you can see these blue or light blue or orange curves are the degradation of the moment capacity with time. And you can see that, for example, for sulfate attack, you can expect a service life between 50 and 60 years, depending whether you consider or not a superposition between erosion and leaching, whereas you have a much longer service life in the case of chlorides because you have initiation period so that the chloride had to arrive at the critical level and then you can start the corrosion. But then we said that this material heal. So how can we take into account the healing of the material into the durability? So we performed an extensive experimental campaign. You can see the evidence of crack healing. We also evaluated the recovery in water permeability. You see this homemade setup that we built up and used during the lockdown, where also the access to the lab was not fully available. So we had to comply with homemade equipment. And we evaluated, for example, this is crack sealing, the crack closure. So you can see that a long time, up to 6 months, we evaluated, you go to up to 80 or 90% of crack closure. And also the recovery of stiffness, which is on the graph on the right, well, it's less performant, but you still can go to about 40 to 60 recovery of the stiffness, which turns actually into recovery of damage. Interesting thing is when we use the nanoparticles, here are some results with the crystalline admixtures and the alumina nanofibers. You can see these blue dots on the left graph, they are really in the region of very narrow crack width. So the alumina nanofibers were able to interact with the microfiber reinforcement in a synergy to keep the crack width very, very low, around 10 microns, and to guarantee the best self-healing capacity. And there is also a comparison on how these also worked curing the specimens and dealing the specimens under geothermal water. You can see that these blue and red and green dots, which are the material, the experimental data referring to the nanoparticles, are better than the gray one, which are the reference. So what are we doing now? We are trying, in the beginning, we started with the evolution of the resistant bending model just of the critical cross-section. We are now trying to implement this approach into a moment curvature segmental approach and to extend this to the wall cantilever. You can see here the scheme. So we have the degradation mechanism. We implement it into a cross-sectional model, and we calculate a moment curvature relationship as affected by degradation. And by integrating this twice over the beam length, we can calculate also the displacement. So these are really quasi real-time elaborations. I have PhD student and a couple of master students working on this. We have the maximum resisting moment as degrades over time, and the displacement up to 56 years. How do they evolve? And you can see on the bottom right as starting from a 60 millimeter cross section, you progressively degrade, but the degradation is higher at the bottom because there you expect a higher crack and so a higher penetration of the aggressives. And we are also validating these assumptions with a dedicated experimental campaign, quasi unique in the literature, where the material is going to heal under load, which is quite unique because most of the results that you find, the material heals, but with no load at all. So the results have been elaborated in this sense. This is a Rosette diagram where you can compare the expected service life for different mechanisms, cracked or uncracked, healed, leaching, and erosion. And when these points that are put into this diagram, end of structural service life, what does it really mean? Well, first of all, we have to be used to start thinking in a life cycle perspective. This end of service life may turn into reduced maintenance, and we performed a preliminary investigation. And you can see there how all the 7 indicators for environmental impact of our construction can result into significant benefits. For example, abiotic depletion and a reduction in the use of fossil fuels up to more than 60% or even 70%. But also, we have started a pilot study in order to bring to a new life these materials. So we crushed the specimens from our lab investigation, and we used them to produce a new UHPC, and you can see the results. These were obtained by 2 labs, University of Malta and University of Valencia, blue in Malta and red in Valencia, the columns. And you can see that with respect to the reference, whether you replace 50 or 100% of aggregates or of aggregates and fibers in different fractions, you really are able to keep the performance. So this has been a really collective work with a wonderful crew of collaborators and students in Milano at Enel Green Power, who gave us the site to construct the pilot. Stress is an engineering firm who performed the life cycle analysis. I already mentioned University of Valencia and Malta, where part of the study on recycled aggregates was done, and the companies who supplied us the micro and nanoscale additions. So I want to thank my students and co-workers, 2 pictures of how we were 1 year ago and how we were now. And this is the Resilience Project Consortium, once again, hoping that we will be able to be back to meeting in person soon. And I also invite you to visit us on our website, www.uhdc.eu. Thank you for your attention.